Okay, let's go back to perturbative QCD, please.
All right, so this morning we were talking about E plus E minus goes to hadrons, and we'll come back to this picture as another thing we'll discuss in a little more detail. We had these two questions that I raised at the end of the lecture. One was, we did a calculation with quarks and gluons. In perturbative QCD. And we got this result at the very bottom of the board here that the cross-section is the tree-level cross-section with an alpha S correction that has a very simple form. And the question was, how are we really allowed to compare that to a cross-section for hadrons? And it turns out in this particular case, this is a question that we can actually answer pretty rigorously. It's a little bit, making it rigorous makes it a little bit too restrictive, and I'll slightly generalize what I'm going to say by the end of this example. But in this particular case of E plus T minus, we can use something called an operator product expansion to explore this question. So the next topic I want to talk about is the operator product expansion for this process of E plus E minus goes to anything. Okay, so first of all, what do we mean by an operator product expansion? So in quantum field theory, an operator product expansion, or OPE for short, is the idea that if I have two operators, say J1 and J2, separated by some space-time distance x, then as I take the limit that x goes to 0, the two operators are coming together and they give another operator. When the operators come together, really all we know is the quantum numbers of the operator. And coming together or expanding about the limit of x goes to 0 really gives us a set of operators where the operators are at space-time point 0, and then there's some coefficients. So this idea that I can make an expansion of two space-time separated operators into a set of local operators and coefficients is called an operator product expansion. And this is something that you may sound fancy, but it's not too complicated if you think about the following example. Say we just had W exchange, and we can do this even with leptons. So say we had muon decay. Muon goes to a muon neutrino, electron to E bar. So this is an example with two currents, one here, J1, one here, J2, separated by this W propagator. And if we expand in the limit of p squared much less than mw squared, that is like, in momentum space, the analog of expanding with x goes to 0. And so what happens in that limit is that this localizes into some coefficient, goes like 1 over mw squared, and then an operator, which is a 4 fermion operator. And that's the Electroweak Hamiltonian, what people call the Electroweak Hamiltonian, Fermi's theory of electroweak interactions. And this is actually used when people study low-energy interactions, both in things like muon decay as well as in B decays, where you integrate out the heavy particles, the W boson. Okay, so this is just one simple place where you may be familiar with. We can also use an operator product expansion for this example of E plus E minus to hadrons. And really what we want to do is explore the use of unitarity. So unitarity, or probability conservation, connected to something called the optical theorem, or implies the optical theorem. And that says, so we'll start setting things up using the optical theorem. And what does the optical theorem say? It says I can calculate the cross-section, if I want the total cross-section, as the imaginary part of a forward scattering. So instead of considering E plus E minus goes to hadrons, let me consider E plus E minus goes to E plus E minus. And then inside, I'll allow various fluctuations to happen, including, for example, coupling to a quark loop. And if I just had that quark level diagram there and I took the imaginary part, this is like squaring, okay, the two tree-level diagrams. So that's exactly giving us, and integrating over the phase space of the final state particles. So that's exactly giving us back kind of the picture that we had before for how to calculate the cross-section as a square of a matrix element, except this time we're calculating it by first calculating this loop diagram and then taking the imaginary part. Okay, so now, though, let's generalize this to sort of allow anything to happen in the middle. So this, we can be quite general about this. We don't have to work, at this point, we don't have to work in perturbation theory. We just say anything's allowed to happen there. And that means that if you think about what we're looking at here, we're looking at a vacuum polarization tensor for the photon due to hadrons, or hadronic interactions, due to the coupling to quarks. So what this is, up to some prefactor, is the imaginary part of the vacuum polarization tensor, pi h, where pi h is defined prefactor as a time order product of two electromagnetic quark currents. Okay, so these are the currents right here that I know are there that are coupling to the quarks. But then what happens after that, I'm leaving kind of completely free, and taking this vacuum matrix element is giving me this vacuum polarization tensor that couples to the photons. I've contracted the indices here just for simplicity, but they would be coupling to the photons, the mu indices there. And if you look at the dimensions of this quantity, this is a useful thing to do. So the dimensions of the x here are -4, because the mass dimensions of x are inverse to momenta. There's a q squared downstairs, which is -2. These are quark currents, electromagnetic quark currents. So what I mean by this J is it's the electromagnetic charge of the quark, then just a vector current. And so the dimensions of this are just the dimensions of the quark fields, which are 3/2 each. So each of these is +3. The vacuum is dimensionless. The phase is dimensionless. So the overall dimensions of this quantity is dimension 0. Okay, so that's just something that's useful to know. And what does it mean now? We've got a product of currents, J of x, J of 0. So that's something we can consider doing an operator product expansion in. So what would that operator product expansion look like? Well, this is just the Fourier transform of the type of formula that I wrote down here. This was in position space, two currents, space-time separated, position space function, Wilson coefficients multiplying operators. And so the only difference is we'd Fourier transform those coefficients to momentum space. So the reason that we're interested in looking at the dimension is because we have to write down operators with the right dimensions and the right quantum numbers. And actually, in this case, the simplest operator with the right quantum numbers is just the identity operator. It's dimensionless and has. And so what this is an expansion in is an expansion in the dimensions of operators, where we start with the lowest dimension operator and then we go to higher dimension operators. So we could have psi bar psi as a higher dimension operator, or we could have g mu nu as a higher dimension operator, et cetera. And this will be valid if our pi h of q squared is dominated by short distance. So we are making an assumption here that we have to come back and talk about. Make this type of expansion, we're making an assumption that the correlator is short distance dominated. Okay, so let's proceed under that assumption for a minute, and then we'll come back and try to be a little bit more rigorous about that assumption. So if we think about this pi h of q squared, This is kind of at the, what I've written is a bunch of operators, but then I take the vacuum matrix element of them. So I left that out. There's a vacuum matrix element of this expansion. And the vacuum matrix element of this identity operator is just giving 1. So at this level, there's nothing showing up that depends on any hadronic physics. At this level, you're getting some condensates. And those condensates, if you're just taking them in the vacuum, the only quantity that can set the scale for them is lambda QCD. So if you look at the dimensions of these objects, this is dimension 4. So this is going to give something that's order lambda QCD to the 4th. And this is given by m lambda QCD cubed. And then these coefficients have to make up the dimension to make it dimensionless. So this coefficient is going to have a q to the minus 4, as is this one. And so these two terms here, which do have some dependence on hadronic physics because of the lambda QCD showing up, are suppressed because they're inverse powers of q squared. Whereas this coefficient here is just dimensionless all by itself, and there's no lambda QCDs showing up because this is the identity operator. No. So we're making a separation of the scales q squared and lambda QCD. And the short distance scales are in the coefficients, and the long distance scales are in the operators. So that's why. And that's exactly like over here where we had 0, right? Okay, I mean the x is here and the 0 is there. The 0, you're going to take a matrix element of this thing, and that's going to be the place where you get long distance physics. This coefficient is universal. It didn't actually depend on what matrix element I even took. I could take a vacuum matrix element or some other matrix element and use this operator product expansion. But that's a good question. C1 is some function of q squared, but just not an operator or anything, just a number.
Depends on q squared. Sorry. If it depends on q squared, which scale do you use?
I'll tell you how to calculate it in a sec.
Okay, thank you.
Okay, so these two here are suppressed, and that C1 is the dominant thing. And so how would we go about calculating C1? Well, we could think about calculating C1 with quark and gluon diagrams. So to calculate C1, or more properly the imaginary part of C1, we would set up a calculation where we take our operators and we just start looping up the quarks. We send in Q through this loop diagram, and we take the imaginary part of that. And if I take the imaginary part of that, that's again an integral over the phase space of this times the complex conjugate. And that's exactly giving our cross-section. This is what happens at the lowest order, and then at the next order, you'd have the imaginary part of a diagram with the gluon in it, which could be that one or of this one. And if you start taking the imaginary parts of these, meaning cutting these diagrams, then that's giving back exactly the square of those loop diagrams that we talked about in the last lecture. So for example, if I cut it like this, then I have the virtual diagram multiplying by the tree level diagram. That was one of the terms in the square that we talked about. Or I could cut it other ways. Like this, and that would be one of these final state emission diagrams. And this would be another one. Those would be the real contributions that we calculated. And actually, this is a nice way of even doing the computation because you'd add various contributions first and then take the imaginary part at the end, and that allows certain cancellations to occur ahead of time. But the upshot of this is that this calculation of this coefficient exactly reproduces our quark and gluon level calculation. So saying that we have an operator product expansion is separating the long distance physics in these operators from the short distance physics in these coefficients. For the short distance coefficients, we can do the calculation with quarks and gluons and know that that's okay. And we see that it reproduces our Fork-and-gluon level calculation. So if this operator product expansion is true and this term here dominates, then we get back the idea that we can do the calculation the way we outlined and use this result. But we still have to address this if. Okay, so how do we address the if? So to address the if, in this case, we can study the complex structure of this vacuum polarization. What is the analytic structure of this? So we look in the complex Q-squared plane. The analytic structure of pi h. And in the complex Q-squared plane, this thing has an imaginary part corresponding to the real particles that are the hadrons. And that's a cut along the real axis here. There's a cut there, and that's basically it. Okay? Now, the tricky thing about the OPE, though, is that if I were to pick any point on this cut, which is where I'd like to do the calculation, I'd like to take some large q squared, this is real q squared, I'd like to take some large q squared point, then I'd be sitting on this cut. That's where I'd like to do the calculation. That's where I want my pi h of q squared, but that's not where the OPE is valid. Let me make a note of that first. Where is the OPE valid? Well, when I take this limit x goes to 0, really what I'm doing is I'm thinking about a Euclidean point going to 0. And that means that the OPE is valid not over there, but over here in some negative q-squared region, like some large Euclidean q-squared, so negative q-squared here. X Euclidean goes to 0, so q squared equals minus some q squared. That's where the OPE is valid. But thankfully, there's relations between the physics in the complex plane due to complex analysis. So to see that, let's take a contour integral. Looks like this. And they'll just think about integrating that along that contour. Okay, well, to make things interesting and to introduce this point q0 squared, let me do the following. Let me think about the following integral. And it's not the unique thing that I could think about, but it's sort of a simplest thing that I can think about that converges at infinity and has all the properties that I want to look at. So let's just introduce a double pole, q squared plus q0 squared. I introduce the square to get convergence out here at infinity, so I don't have to worry about what's going on the contour there. And then I can evaluate this integral two different ways. One way, by shrinking the contour down to this pole that sits here. And if I do that, this is a double pole, so I have to take a derivative of the numerator. So I take derivative of d pi h dq squared, and then it gives a simple pole, and that's the residue theorem. And this I can calculate in the OPE because I've shrunk my contour down so that it's wrapping around this point, and it's in the region where the OPE is valid. So I can use the OPE for that. And then I can do another thing. I could just look at this contour as I drew it. And if I look at the contour as I drew it, I just integrate along the contour. And I told you that the contribution out at infinity was dying off because I had enough powers of q squared in the denominator. So if I extend my contour out to infinity, really where I'm getting a contribution from is just this fact that there's this cut here, which is blocking me. And I can come as close to the cut as I want. So really what I have is two paths, one above and one below the cut, but in opposite directions. And what that gives is an integral along the cut along this real axis from some place where it starts, which is actually related to the pion mass in this case, say, or the rho mass, some mass. Depends on what currents I'm considering, of the discontinuity of pi h of q squared across that cut. And the discontinuity of pi h of q squared across the cut is just 2i times the imaginary part. So discontinuity is just the imaginary part across the cut. And that imaginary part of pi h is just related to the cross-section. So really what we have here, putting in some prefactors, is an integral over the cross-section. Reversing it and writing things back in terms of the cross-section. The cross-section was a function of q squared. If I integrate the cross-section with some weight factor along this cut, that's related to something I can calculate over here. That's what the OPE says. Okay? So this I can calculate. And of course, I can vary this Q naught, so it's not like I just have a single piece of information. I can change the Q naught and get more pieces of information. And I could even change this weight factor to weigh the cross-section in different ways. And this I can calculate. And basically what's happening is, in this expression, I'm averaging over hadrons. Okay? And in this expression, I'm summing over partons, quarks and gluons. And the whole statement of whether the two calculations are going to agree with each other is, did I average enough? If I try to compare point by point, like at a very particular point, at one point on this cut, and it's not necessarily going to agree, but if I average over enough, and in this integral I've averaged over the whole cut, then the two things are comparable rigorously. And that's what the OPE tells us. So the moral is not that I have to necessarily average completely over the cut as I did in this example, but I need to average over enough states if I'm going to make a correspondence between hadrons and quarks and gluons. And that's really the moral of this calculation, sort of a more general lesson than the precise results of the calculation. So we need to average over enough states to get agreement between our quarks and gluon calculation, our perturbative QCD calculation, and hadronic cross-sections. And this is what's known as quark-hadron duality. That they will be related if I do enough averaging. And if you actually look at the data, you see that you could have convinced yourself that that is necessary. So let me give you a picture for what the data looks like. Because the data is going to have resonances. On this cut, there are states that are just hadronic states that open up, and then there's a resonance. And nothing in my perturbative QCD calculation necessarily will get the structure of that resonance right. So if I plot the cross-section versus q squared, and I'm doing this around the charmonium, just for illustration, there's going to be charmonium resonances. And these are spikes in the cross-section that look like this. Smaller spike. Okay. Something like this. And eventually it gets smooth because the number of states is getting so large that the fluctuations are averaging out. And what our perturbation theory results is going to look like is some smooth curve like that. This is PQCD. This is the hadronic cross-section. And so on average, the two can agree. In particular, I better not compare pointwise in this region, or I'm bound to find a difference. But if I average over a large enough region of order several GeV, so the units on this axis are like 3.5, 4, 4.5 squared. If I average over several units of GV, then I can get agreement between the perturbative QCD and the hadronic result. And if I'm out in this tail, I can make a further approximation where I could just say, well, look, my experiment has some resolution. It's always going to be binned. And at high enough Q squared, then even just the binning in the experiment might be good enough. There might be automatically enough states in that bin that I'm doing and averaging. So as I go to higher and higher Q squared, I can make the bin size a bit smaller because there's more states in there. And therefore, at large Q squared, you can even think of comparing pointwise. And that's called using local duality. Okay, but that's the connection between hadrons and gluons. So it's not true in general that they're just going to be equal. We have to be careful to sum over enough states on the two sides. Okay, so that was one of the questions that we wanted to address. And so the other so I'm now going to switch gears. So if there's any questions about this, it's a good time to ask. Okay, so the other question that we wanted to ask is if I went back to this cross-section level formula, what happens if I start putting restrictions on my real emission cross-sections? Okay, so that was the second question. And to address this, I'm going to talk to you about two different approximations in QCD that are quite useful, even more generally than just answering this question about E plus E minus to hadrons. And that is what is known as the soft approximation and the Colinear approximation. So we'll use these approximations in the context of thinking about this question of phase space restrictions and what happens, but we'll find more use to them than just that later in the lecture. Okay, so if we put cuts on the phase space, what's going to happen is there's going to be some parameters involved with those cuts. And our 1 over epsilon poles that we have in the result on the left are going to be accompanied by some dependence on those parameters, and in particular, logarithmic dependence on those cutoffs. Okay, so let's see how that comes about in two different approximations. So first, what's called the soft approximation. Okay, so what is the soft approximation? So I could consider some amplitude A0 that emits some energetic parton, maybe it's a quark, and then I have some soft parton, which is a gluon. Its momentum decay, 1, say, so this is 1 plus k. And if I want to look at the limit of k goes to 0, that's the soft limit. And I want to see what kind of approximations I can make for an amplitude like this one. So if I just look at this part of the amplitude where the k is coupling to the fermion, I've got some spinner for the fermion. I use now my Feynman rules that we wrote down last time. Polarization vector for the soft gluon. And I have fermion propagator. And then I have the rest of the amplitude, which I'm just calling A0. And if I make this approximation that k is small, one thing I can do is I can just drop this k here. And then I have a P1 slash, and I can push that P1 slash through the epsilon slash here so that it hits the spinner. And U bar 1 times P1 slash is 0. That's the equation of motion. So the only term that I get is the dot product between these in the numerator. And in the denominator, I can write it out. P1 squared is 0. I have 2P1 dot k, and then I have k squared. And k squared is much smaller than 2P1 dot k, so I just keep the 2P1 dot k. And therefore, this factor here that sits between the amplitude and the spinner is just the coupling. And in the numerator, I have P dot epsilon. In the denominator, I have P1 dot k. And then there's the color matrix still, of course. And that approximation that is the soft that's the result of the soft approximation. It's also called the Connell approximation. The Connell approximation is given by this fact that we have these linear propagators, and then that the polarization tensor is also just dotted into the P. And it's a more general approximation than just this simple case here. For example, we could apply it to n partons. 1, 2, 3, 4, 5, all the way up to n. And the result would just be that I independently add the particles to the external lines, doing the same thing that we just did here. In this case, the color representation of the different lines can change. Let me call it T sub I. So it depends on the color, on the representation. Some of these could be gluons, some of them could be quarks, for example. But the basic structure is the same. It's a P dot K downstairs and a P dot epsilon upstairs, and I just sum over all of them. And then I act on something, which is the lower point amplitude. So this is an amplitude with n, capital N, partons, and what I've done is I've added somewhere one of these lines, soft particle. So this is a kind of factorization where I have an amplitude that has n plus 1 particles, and it's factoring in terms of some prefactor times an amplitude that has n particles. So there's amplitude n plus 1, soft factor, times amplitude n. And in this soft factor, there are non-trivial color correlations that are determined by these T matrices. So it's not completely just a multiplicative thing. There's some color correlations encoded in those T's. Okay, but nevertheless, we could just take this approximation and apply it back to our example over here, our calculation of the sigma r hat. Let's think about calculating sigma r hat in the soft gluon approximation. So the first thing we'd do is we'd go through the amplitude and figure out what the amplitude would be, and it would give this form P1.P2, and then P3 was the gluon, so here K is P3. We'd have linear propagators like this. That would be the amplitude that we'd integrate. So this is the integrand. And then we have our integral over the x's, and I want to make sure that that integral is soft, so let me restrict x3 to only go up to some small delta. Delta is some small parameter. And what that means in the picture over here is that I'm just restricting myself to this little triangle here. So this distance here would be the delta. Okay? Remember that x3 is the distance, this is 0 for x3, and then 1 for x3 is here. So if I'm demanding that x3 is small, I'm saying I'm close to this here, and if I just think about making a restriction on x3, I'm just up in that little corner, which is exactly the soft region where the approximations are valid. So if I go back and repeat the integrals that we talked about last time, but now doing this, I get what I would call the soft approximation to the real radiation diagram, which is basically the same kind of prefactor. It gets the 1 over epsilon squared pole infrared divergence right. There's an extra logarithm showing up, log squared, and then there's some different finite piece. So this is what it would look like. And this is the idea that these 1 over epsilons are now coming with logarithms of that extra cutoff that ensured that I was in the soft approximation. Okay, so in the soft limit, that's where this 1 over epsilon squared came from. And the 1 over epsilon squared that I had in the calculation over here, it got reproduced by just that approximation. Okay, so that's one type of approximation. The other one that we can make is called the Colinear approximation. This one is a little more complicated from the kinematic point of view. So to do this Colinear approximation, we have to do something called a Sudakov decomposition. So what we want to do is we want to consider the limit of two particles going collinear. And so let me draw a picture again for this. So same type of picture we had for the soft, where I have one particle coming out, and then it splits into two, except I'm now doing a different approximation on the two particles there. So let's call this one P1, we'll call this one P glue, and I'll call this P1 glue for the sum. And the Sudakov decomposition is about how do I take the limit, what is precisely my mathematical definition of the limit as these two particles become collinear. So P1 glue is P1 plus P glue for definition. And this is the Sudakov decomposition. I'll just write it out and then I'll explain it. So we want to decompose the momenta in a way that we can take the limit. And the nice thing to do is to decompose them in terms of light-like vectors. So that's what the Sudakov decomposition is. So the P and the N bar that are showing up in this formula, which I'll define for you momentarily, are some light-like vectors. And then the K transverse is, K perp is some transverse vector to those light-like vectors. Two. So I'm going to define the light-like limit as being the limit as the K perp goes to 0 in this decomposition. And what I've done is I've projected onto this P mu, which is a light-like vector, that's defined in terms of the parent momentum, P1, that, and then N bar is just another light-like vector, which I define because I need something orthogonal to this one. Light-like vectors are not orthogonal. They square to 0, so you need some other vector that can dot into them to get something non-zero. So we could just take this, for example. These vectors satisfy P squared 0 and N bar squared is 0. So this is just some general decomposition and some coordinates that I can make of these four vectors. And the Z in this formula has the interpretation as the energy fraction. So it's basically P1 0 over P1 G0. So I can think of it as like this guy carried some energy and it split into these two lines. This side has Z and this side has 1 minus Z of that energy. That's the interpretation of the Z. And then the other thing is that you can work out is you can add these vectors and square them and simplify, and then, okay, you'll get this formula here. And the collinear limit is then defined as K perp goes to 0. And so as I take K perp goes to 0, this P1 and the PG both go onto the same light-like vector. So they're mapping, they're parallel to each other, and that's sort of what we intuitively said the collinear limit should be. There's some non-zero fraction of the original energy that they can each carry, and that's an arbitrary thing that the collinear limit doesn't specify. These terms here, you could ask, well, why are they so complicated? They're just stuck in there to make sure that these vectors square to 0. So these terms just ensure P1 squared is 0, as you can easily check. P squared is 0, and N bar squared is 0, so there's a cross term that's non-zero. That cross term has to cancel this term squared. And they're defined so that P dot K perp and N bar dot K perp are 0. That's how transverse is defined. Okay. So that's the collinear limit. And what happens in the collinear limit is there's also a factorization. So you can see that the P1 G squared in this collinear limit goes to 0. So it's like this particle is a final state particle that has 0 P squared, just an external particle. And so that's kind of a motivation for thinking, why the following formula that I won't derive for you might be true. So if I have some amplitude of n plus 1 particles and I consider this limit, then it factors into a product of a collinear factor times a lower point amplitude. And in this case, I'm squaring the amplitude and I'm summing over spins. And that's giving me a scalar function out front. Okay, so this is a collinear factorization. Similar to the soft factorization, things split into a simpler thing times a lower point function. And then there's some function of, there's a 1 over pg squared. Well, that's just the propagator here. So that's obviously there. That's kind of where some singularity is hiding in the collinear limit. And then there's an arbitrary function of z. Well, it's not so arbitrary because I can calculate it. This thing is called the splitting function. Arbitrary until I calculate it. So I can either do it in epsilon equals 0 dimensions or in epsilon dimensions, so I'll give you slightly more general result. 1 plus z squared over 1 minus z, and then there's an order epsilon term as well. So this is called the quark splitting function. It's the probability that the quark splits into another quark with a momentum fraction z from the emission of this gluon. So again, there's a factorization here. Okay, so we can just take this formula and again, go back and apply it to our calculation of the sigma r hat, just like we did in the soft approximation. So let's take this sigma r hat and make a collinear approximation. So P1 parallel to P3. And the z, in this case, is like 1 minus x3, if we're talking about x3, because z is the quark momenta. 1 minus z is the quark energy. Z is the quark energy, and 1 minus x3. X3 is the gluon energy related in that fraction. Okay? And we have to put some restrictions on the phase space. So I better make sure that I'm in this collinear region where P1 is parallel to P3. And that actually means that x2, if we go back to the picture, is close to 1. Right? I'm along this edge here. And that means I'm along this edge here, and that means x2 is close to 1. So I want to be within delta collinear of 1. That means I'm between those in that little thin band. And if I don't want to double count with the soft region, then I better do something to cut off the integral on this line here. So I can impose that cutoff as well, just to avoid double counting. That would basically mean that I can think about the x3, but I have to only consider the part that I didn't consider before. So that would be this part. So this first part is the collinear constraint, making sure I'm in a collinear region. And this is avoiding the soft region, which we've already accounted for with our soft approximation. So I can go back, make this approximation, make this approximation on my amplitude, which changes it, and do the calculation again. I think I just have enough room to fit the answer in here. So sigma r for P1 parallel to P3, well, there's still a CF alpha over pi. There's a factor of a half out front. And then this just has a single 1 over epsilon pole, and then it has dependence on the cutoffs again. A little bit more lengthy expression. Some finite constant that I'm not writing. So it looks like that. This is only P1 parallel to P3, so there's going to be another contribution from P2 parallel to P3. And once that by symmetry is going to be exactly the same as this. And so this factor of a half is going to go away. This goes away once I consider adding P2 parallel P3. So that's why I pulled it out as a factor of a half up front. And then if I look at the remaining pieces, I have this 3/2 epsilon, 3/2 divided by epsilon, and that's exactly matching up with my 3/2 epsilon here. So we're seeing that this 1/epsilon pole is coming from the collinear region. And if I look at it further, I see, well, I induced this extra 1/epsilon with a 2 log delta, but I had a similar minus 2/epsilon log delta here, and those two cancel. The 1/epsilons are going away, and then I'm just left with some logs of these various cutoffs that I made, and the approximations that I made. Okay. So how should I interpret these approximations? So in some sense, what I'm telling you is I can just calculate the integral in this shaded region. That's what we just did. We add up the various contributions, we're getting the integral of the sigma r, but in this orange shaded region. And last time I told you that in that orange shaded region, we can't really distinguish that this has 3 particles in the final state. It looks like it only has 2. Because either one is too soft to observe or they're too collinear to observe. So we think about it like a 2-jet event. And so actually you can think about what we've just done is put restrictions that force us into a 2-jet region. And we can think of this calculation of these cross-sections as the 2-jet cross-section. So if I think about the one-loop total result, I want to divide it into a 2-jet piece and a 3-jet piece. And let's define that to be the piece in this orange region is the 2-jet, which includes the virtual contribution, and then the rest is the 3-jet. So by this convention, in terms of the objects we have, well, the virtual lives on the edge, so that's in there. And then I just have these various approximate pieces that we talked about. And I can take that to be the definition of the 2-jet cross-section. And when I add up the various contributions, all the 1/epsilons again canceled. But now I'm left behind with logs. And those logs are sort of a leftover reflection of those infrared singularities. They're showing up because those infrared singularities were there. Okay, I won't write it all out again, but it's all those logs that we had. 2 expressions once I add things together. And then sigma 3-jet would just be defined by using the formula at the top of the board, so it's the total minus this formula. So it's also a well-defined expression. And I can think about those as the total cross-section to go to 2 jets or 3 jets, divided up now with this resolution parameter. This is very analogous, actually, to how jets were first defined. So back in '77, Sturm and Weinberg did what are called Sturm and Weinberg jets, and they defined them exactly like this with some hard cutoffs. It's not how we deal with jets nowadays. We have more elegant techniques than hard cutoffs like this, but this is kind of like the classic result of how you would think about jets. Now, it should be noted that these are exclusive jets. I'm really dividing up the events into 2 jets and 3 jets, and I'm asking for the total number of 2 jets and total number of 3 jet events. Okay, I've just made a simple binning of the cross-section into 2 pieces. There's another way of thinking about cross-sections, which is inclusive jet calculations. And in this case, I just ask for a jet with some particular phase space. It's a little bit different. We ask for a jet in a region away from the boundaries with some particular phase space values. So some, in this picture, some values of x1 and x2. So I just ask, what's the cross-section here? And if I'm away from the edges, then I can trust my perturbative QCD calculation, and I can just think about calculating that in terms of x1 using the distribution, which is perfectly well behaved away from the edges, this x1 squared plus x2 squared over 1 minus x1, 1 minus x2. could just use that as my jet cross-section. So that's what's called an inclusive jet calculation, whereas this is like an exclusive jet calculation, and both of them are used. Both of them are measured. So both of them are kind of useful terminology to have. Okay, so this is kind of an introduction to the ideas of jets based on our E plus E minus calculation. I want to talk now a little bit more about really how jets are defined at the LHC and other colliders. We'll come back to these approximations, and we'll use them a little bit, particularly the Colinear one. Okay, so there's two questions we need to ask and answer. First of all, we didn't actually really explain why there are jets. We've kind of hinted at it in various different ways, but let me spend a few minutes on that. So let's first question, why do we get jets? That's basically because in this Colinear approximation, things are enhanced. So we get log enhancement from the Colinear limit. So if I think about, again, my splitting function calculation where we have the Colinear limit, and we have some P0, and there's 1 minus 0, z P0, and z P0, this energy fractions that we just talked about. The cross-section is proportional to this term that comes from the splitting function. And I can write that in various different ways. I wrote it as this 1 over PG, 1g squared, but I can also write it as a 1 over k perp, or dk perp over k perp, once I put the phase space together. It's just another choice of variables. And so I can think of this cross-section as proportional to something with that splitting function, and then a dk perp over k perp, which is that 1 over p squared type singularity. It's like dq squared, or dp squared over p squared. And this is giving an enhancement. It's giving a logarithm that enhances this cross-section in that limit. And it happens not just for quarks, but also for other things. So if I had two gluons, similar story, this becomes a Ca now instead of a Cf. Bigger, and then this is k perp over k perp. And there's a different function here. The splitting function for gluons has a different functional form. 1 minus z over z, z over 1 minus z, plus z 1 minus z. Okay, but there's again a logarithmic enhancement from the Colinear limit. And similarly, we have, okay, if we ask about the gluon instead of the quark, this gives a splitting function that's pgq of z, or we could start with a gluon and then get a quark. This gives something called qg. So the parent is on the right, and then the daughter is on the left. Okay, so these are different splitting functions. My notes, I wrote down what those splitting functions are, but I won't write it on the board. So the radiation prefers to be collinear because there's a log enhancement. That's the upshot. All these amplitudes have a log enhancement from the dk perp over k perp. And since it's preferentially collinear, that's what leads to this shower of hadrons. And if you ask about the leading contribution actually comes from what's called a strongly ordered limit. So if I started with some K1 perp, and then I had a second emission at some much smaller perp, et cetera, down the line, until I get to some K perp, the nth one, which is, say, of order lambda QCD, and then there I better stop because that's when hadronization is going to happen. I'm basically going to shower as long as I can, all the way down the line while I have this strongly ordered hierarchy. And the reason that that's going to happen is because even though I get an alpha S for every emission, if I've got ki plus 1 perp divided by ki perp, and these are strongly ordered in the sense that one's much bigger than the other, this logarithm can compensate for the alpha S. And so this could be of order 1. And then there's no suppression to the emissions. So we get multiple, so even if this is large, if it's 0.7, we have high probability of having multiple emissions. And that's what's producing the shower. Okay? This is our picture for why we're having this shower of particles that are forming the jet. This is the shower that gives the collimated jet. Okay, so the Colinear Approximation is at the heart of why we get these jets. There's also soft singularities that we could talk about. It's a little more complicated, so I'm not going to. There's soft singularities in the Z integral here. There's something called angular ordering, and that actually has some I don't want to go into the details, but that has some relation as to why the soft particles aren't sort of destroying this simple picture of there being a jet. But suffices it to say that the singularities of QCD prefer to have collimated radiation in the way I've described. Okay, so that says why do we get jets? The other question that we need to ask is how are they precisely defined if they're not defined with these hard cutoffs like I did? The hard cutoffs is perhaps the most intuitive definition, but it's not really a good algorithmic definition. Once you start having many, many jets and the phase space gets very, very complicated, you don't want to have to go in and look at that phase space and draw an n-dimensional figure and think about the boundaries, right? And how am I going to put cutoffs on that? And you would have to keep doing it, and it would be different at each n, so that's not very useful either. So how do we do something more elegant to define jets? You see, there's not a unique definition to the jet. If I move my cutoff, nobody told me that I couldn't move my cutoff to the left a little bit and enlarge the 2-jet region and shrink the 3-jet region, right? I just have a parameter that tells me what I mean by 2 jets, which was this cutoff. So it's not, the jet definition is not unique, but we want to answer the question of which particles do we group together. It's a non-unique question, but we should come up with some reasonable algorithm to do that. And so one thing that the algorithm better satisfy is what's called infrared safety. So that means that where these infrared singularities occur, if I have some kind of infrared process where it's collinear or soft, it shouldn't change the outcome of the algorithm. So whatever the result of the grouping is, it should be invariant under a splitting of pi goes to pj plus k in the case where pj is collinear to pk or one of them is soft. That's a condition I'm going to impose on the algorithm, that it has this property of infrared safety. And in general, there's a long history to this, and it's rather complicated, and I'm not going to go through that history for you, but I provide you some review article that does. I will provide you when I give you references, which I haven't posted yet. Okay, so in order to describe to you how this works, I have to actually take a little bit of a detour and talk about some variables, because I'm going to write down the algorithm in terms of some variables. I need to talk a little bit about Hadron Collider variables and what are even a good set of variables to use. So when we're talking about a hadronic collision, there's some axis which is the beam axis, which we take to be the z hat axis. Okay, so the beam is along the z direction. And then perpendicular to that, we have px and py. And if we have some 4-vector in this space, or 3-vector in this space, then we can make the following projection. We can project it onto this plane that's transverse to the beam. Okay, and that's going to make some projection down onto this plane. give this vector here. And this is called the transverse momentum, the magnitude of this vector. And then there's some angle, which we usually call phi. So the variables pt is the magnitude of the vector in the transverse plane, which is the xy plane, and phi is the angle in that plane. And the other thing that we have is this theta here, but we actually don't like to use theta. So we do like to use transverse momenta. So you often see description of LHC processes in terms of PTs. And the other variable we like to use is what's called rapidity. So it's defined, it's related to the angle, but it's defined in a different way by this logarithm. And this rapidity has a nice property that under boosts along the z-axis, it's simply additive. Because under boost, these things here are multiplicative in an opposite way, and so you get a multiplicative factor inside a logarithm, and that makes it additive. And that means if you take differences of rapidities, like y1 minus y2, these are invariant to boosts along the z-hat direction. So why do I care about that? I mean, maybe it's a nice property, but really do I care? The reason that we care is that in a hadronic collision, you actually don't know the center of mass frame of the partons when they collide. You send in your protons, and you're in the center of mass frame of those, if you've sent them in with the same energy. But out of each proton, I'm going to take a parton. And when we talked about the factorization theorem, there was some momentum fraction to the parton on each side. It was this XA and XB. And they don't have to be equal. So it can be that this guy is a much longer vector, a much larger momentum than the one on the right. And that means that the partonic collision is boosted along the z-axis with respect to the hadronic collision. And if I use these types of variables, I'm not sensitive to how much I'm boosted along, how much the parton distribution functions are providing a boost. And so that's something that we want when we define our jets. We want to be invariant to that. We don't want to be sensitive to it. Okay, so what we're going to use to define the jet algorithm are variables like this delta y, or the phi and the pt. These are good variables. Phi is also good. Okay, so those are the variables we're going to use. And in terms of those variables, okay, I should say, if this, a couple of other formulas, if I'm in a situation where the particles are massless, then this can be written in terms of the angle, and it's just log of cotan of theta over 2, so there's just a mapping. And the type of distance measures that I'm going to use are things like the distance between particles in a theta phi space, but I'm going to do it in terms of y. So I have delta y squared plus delta phi squared. That would be an angular separation, which I call delta r. That would be an angular separation that's boost invariant. And that's the type of thing I want to use to define my jet algorithm. Okay, so those are just some variables that people talk about when they talk about collider physics. So how do we define an algorithm now? Okay, these are what are called recombination algorithms. So they're recursive definitions. So we consider a set of particles, and let me just tell you the algorithm and explain it as I go. So we consider a set of particles L. There has to be that it's equally applicable to experiment and to theory. So it could be partons, quarks, and gluons for theory. It could be hadrons or calorimeter cells for experimentalists. And then we calculate various distance measures between the particles. So if we have two particles, I and j, we can calculate a distance between them. And there's different definitions, but here's sort of the most common set of algorithms that people are using. So we have an angular separation, delta r squared, between particles I and j, which we can weight in some fashion with some parameter r. And then we can also use the pt as something and take the minimum, for example, of the PTI and the PTJ with some power r. And this is just some definition of a distance between I and j. The distance is not a unique thing, and there's two parameters in this that would change the result, little r and capital R. And then I'm going to compare that also with the distance to the beam, which I can just take particle I raised to the 2r power, a distance measure between particle I and the beam. And then what I want to do is I take all particles, calculate these d's for all pairs of particles and particles, and I find the minimum, so this is the algorithm, of all particles in the set of the d's. And depending on the outcome of what happens, which one is the minimum, I do one of two different things. If there's some dij that's the minimum, say dij is the minimum, then I group I and j together because they're nearby, and that's what I want to do. So I take I and j and form a new particle and stick that particle in L. And then I just repeat. So now I've got a new L. I've gotten rid of that particle. I've got a new particle. And then I go ahead and do the same procedure again. If this guy is the smallest, then the particle I is close to the beam. So at this point, I'm going to call I a jet and then just remove it from the list. And then I repeat again. So this is something I can do over and over again. I keep changing L. I keep removing particles, and either remove them by calling them a jet, and it can be that some get grouped together and then they get lumped out as a jet, or I just keep grouping them together into sort of pseudo-jets that are eventually going to get thrown out into jets. And I stop this procedure when there's nothing left. So I just run it until there's nothing left. Stop when the L is empty. And that's the recombination algorithm. And the various algorithms that people use that you may hear about if you hear people talking about jets are related to the choices of the parameters here. Oh, there's a choice of the little r. And there's three popular choices, 1, 0, and -1. This is what's called the KT algorithm. This one, for historical reasons, is called Cambridge-Aachen, done by people at Cambridge and Aachen. And this is anti-KT. And they differ in exactly how they deal with the particles. For example, the KT algorithm clusters soft particles first. And that's because I'm raising the PT to a positive power, so the smaller of these is going to be the softer, and that's the one that gets clustered first. This guy has the PT downstairs, so it works the opposite way. It clusters the energetic particles first. And this one here is purely geometric. There's no, the PT prefactor is absent, so it's just taking angular distances. And the exact shape of the jets that come out of these is going to differ, actually. It turns out that this last one gives very circular jets. Clustering the energetic particles first tends to give you circular jets, and these ones are more irregular. And different physics applications will deal with these differently. The experimentalists really like this one. They like having very circular jets, and that's because it helps them with pile-up subtraction and removing soft particles, calibrating the energy of the jets, various experimental things. So this is the default, actually. Currently, the default used experimentally is this anti-KT. Okay, so that's definition of jet algorithm. The other parameter is this R, and that is called the jet radius. And it really is a radius in the case of the anti-KT, where you get a circle of radius R. The other ones, it's just a parameter that's still called the jet radius. Okay, so for example, we could say the following. We could say, let's take R equal to 0.5. This is typically we just freeze R to some value. run this algorithm. That's going to tell us how many jets our event had. And then we can do cuts on those measurements. So for example, we could demand that there only be, we throw away events unless they have just one jet. So we do this for every event. And then we just classify the events. So if we wanted one jet, we could say that there's one jet that has PT greater than 30 GeV, and remaining jets are soft, meaning that they have PT less than, say, 30 GeV. And that would be a way of putting cuts on the result of the algorithm that would provide me with a one-jet event. We call that a one-jet event. So after running this algorithm on the events, we can then group them into one jet, zero jet, et cetera. Give you one other example. So a zero jet example is even simpler. Say I had Higgs plus zero jets. This is one that we mentioned already. And this is actually used in the Higgs measurements for Higgs couplings. So here the measurements, the cuts are even simpler. We just say all the jets have PT less than or equal to 30 GeV, which sometimes we call the PT cutoff that defines the zero jet bin. And if you calculate the cross-section in this limit, you're going to have something that looks like the inclusive cross-section, but then because of these cuts, just like the delta parameters that were showing up, you're getting logarithms here because of the cuts. And it turns out that you get a double logarithm of the PT cut divided by the Higgs mass. Do the calculation for this. Okay, so it's not like that story about the logarithms showing up that changes. It's just that the precise structure of the logarithms is going to depend on how you define your jets and how you impose the cutoffs. And in this case, it's this PT cut parameter that's defining my zero jet bin. Okay, so this is a large logarithm. It's actually a large double logarithm. And for PT of 30 GeV, you actually want to sum these logarithms to all orders. So it's not just going to stop at this term. There's going to be higher order terms as well, and you need to compute all of these terms. It has the structure of, for each order in alpha, you get an extra power of 2 logarithms. It looks like that. And thankfully, this is actually pretty simple to sum because it exponentiates. So the sum looks like an exponential of that lowest order result. And that exponential is an example of what people call a Sudakov exponential, Sudakov form factor. Okay, and we'll see why in a few minutes, actually, why that type of term is not too surprising that we get that. Okay, so this is kind of a big change, an exponential of this logarithm. So we can change this thing by an order of 1 amount by putting this type of cutoff. And if we want to make Higgs coupling measurements, we better know that that's there, because if we want to compare, a standard model prediction where we were trying to extract some couplings of the standard model, and we're looking at Higgs plus zero jets instead of Higgs inclusively, we better take this QCD radiation factor or damping factor that comes from putting these strong restrictions on the radiation. We better take those factors into account. Okay, so this brings me to the point in my lectures where I want to talk about the parton shower. So this is, again, something that comes out of the Colinear Approximation. And it's a widely used set of tools that people talk about for LHC physics. And in particular, people use Monte Carlo tools to develop showers like the ones we drew. And why would I want to do that? Well, so far we've sort of said, let's try to make things as inclusive as possible and extract physics from that as inclusive observables. But sometimes you just have to bite the bullet because you really need a very exclusive description of the event. And if you need that, this is the tool to use, parton shower Monte Carlo. And not only does it do this whole showering of the quarks and the gluons, but it also gives hadron level predictions because we incorporate some hadronization model. If we really need that, then there's sort of no choice but to do a parton shower. And so what exactly is it? So it's a Monte Carlo program, meaning probabilistic program, which iterates the Colinear approximation and gives a result for the fully differential spectrum based on just using the Colinear approximation to produce a shower of particles. So typically you would say that you have predictions that are valid at leading log. Okay, this is kind of like what we mean by leading log, the largest set of logarithms, leading log shower. There's also some other technical approximations. One of them is large NC limit. You take the large NC limit, so NC not being 3, in order to drop certain diagrams that are order 1 over, or certain contributions that are order 1 over NC squared. That makes everything planar and much more easily implementable. And then eventually you're going to have to do some hadronization, and you're just going to use what's called a hadronization model for that, to group up the particles into hadrons. So I want to talk to you about, the part that I want to talk to you about is this: how does it iterate the Colinear approximation? So we need probabilities here. And they're related to the Colinear approximation. So the probability for parton I to branch when it encounters at some q squared interval, so we'll go back to using q squared instead of kt as the variables. So if I'm in a q squared interval, I could have used kt, but let's use q squared. If I'm in a q squared interval between q squared and q squared plus delta q squared, dq squared, this is like the q squared interval of the parent, then I'm going to define that to be the probability, dpi, and then I'm using the Colinear approximation for this. So there was that 1 over q squared factor, 1 over p1g squared. So that's the 1 over q squared here. And then there's our splitting function for whichever partons I'm talking about, j and I. And I'm also going to put some cutoffs in order that everything's well defined. Let me just write in some cutoffs on this integral so that I stay away from the singularities. And those cutoffs are put in by demanding that the invariant, if I say that the delta q squared of any two particles is less than or equal to this capital Q squared, then the particles are not resolved, and we better stop. And so we're always demanding, therefore we're always demanding, maybe I should make this else and change the inequality. We're always demanding that delta q squared is greater than or equal to capital Q0 squared. That keeps us away from the edges of our picture and ensures that we never encounter the singularities. And then everything here is just a finite integral that can be done, and then this is providing me with a probability that I can use. So this is the probability, a finite probability for branching. We also need a probability for not branching. Once we have those two things, then we can form an algorithm. So let me derive for you the probability for not branching, given that we know the probability for branching. So let's have a no branching between some capital Q squared where I start and little q squared where I stop. And I'm just going to define that as a notation to be a delta of capital Q squared comma little q squared. And in order to figure out what this delta is, let me do the following. Let's consider the derivative of this delta. Well, the derivative, if I think of it as just a finite difference, this is the limit as dq squared goes to 0 of my delta evaluated with little q squared plus dq squared minus delta q squared comma little q squared divided by dq squared. So it's just a difference of deltas. This is no branching between capital Q squared and Q squared plus dq squared, and this is no branching between Q squared and little q squared. So the difference is this extra piece of no branching with the dq squared. And that extra piece means that there was a branching. So this thing is proportional to the branching divided by the branching probability, dpi, divided by dq squared, and then multiplied by a factor that said at least there's no branching between capital Q squared down to little q squared, and then there's a probability that the extra little piece between these is this dpi. Okay, so the numerator is delta I times dpi. And this is the way in which the no branching probability is related to the branching probability. And this is a differential equation for delta I that I can solve. And the solution, because there's a delta I on the right side, is an exponential that looks a lot like that Sudakov exponential that I just talked about, up to a few small differences, important differences. So this is the way the solution looks. Okay, so that's the solution of the differential equation. So this is the no branching probability. If I was actually to take q squared comma q0 squared, this would actually, I could do all the integrals, and that would reduce to something which is exactly like the Sudakov exponential. So the Sudakov exponential is not unexpected because it's the Colinear approximation is giving those types of exponentials. Okay, the one that we had over there in the jet processes. They're very generic. Okay? But this thing is more differential because it acts between q squared and this little q squared, and I can consider not branching between q squared and little q squared and then having a branching and then consider not branching again. So the way that this forms these are the two pieces that are sort of the key ingredients in the algorithm. And then there's lots of things that are details of how you set up the algorithm. And basically, the way you think about it is you think about having an evolution where you're doing the evolution in this q squared variable. So you have some kind of shower, particles, like this, where you start at capital Q squared for the initial person, or initial guy here, and then you order things in decreasing q squared. So q squared is your kind of like time variable for the shower, how you go down the shower. So you go from capital Q squared to some Q1 squared to some Q2 squared, where they're decreasing. And then eventually you stop the shower when you get to that Q naught squared. And you don't shower anymore. Okay, that was the cutoff. And to do the implementation, it's actually not too complicated, so that I can actually describe it to you. You get a random number that you generate between 0 and 1, call it rho. And you use that random number with the weight given by this no branching probability to determine where is the first branch going to happen. So you solve delta I of capital Q squared, Q1 squared equals rho. You solve that for Q1 squared. And that will tell you where the branching occurs here. And okay, obviously, if the Q1 squared is smaller than if it's greater than Q0 squared, you need to choose a z value, and you use the p for that as a probability distribution to give you a z value, and then you've got the kinematics of this particle. So, and then if this isn't satisfied, then you would stop the shower. Okay, and then once you do that, you would repeat to determine this Q2 squared, et cetera, down the shower. Okay? So repeat. And when you repeat, you would start at Q1 squared instead of Q squared as your initial condition. Would be some other row, and you'd solve for the Q2, and that's how you probabilistically determine the shower. So you're determining how long do I not branch, and then I branch, and then how long do I not branch, and then I branch. And that's determining the shower based on the QCD formulas at leading log approximation, and that's how we build up with this collinear approximation the basics of a parton shower. And so this kind of idea underlies Herwig, Pythia, Sherpa, all the commonly used parton showers, and then they differ in the details, including, for example, what is the ordering variable, whether it's Q squared, KT squared, angles. These are different possible choices for the ordering variable of the shower. And exactly the details of how you implement QCD matrix elements is also sometimes different. Okay, so I'm out of time. That's where we'll stop today.